Okay, next up what we're going to do is we're going to look at the aircraft geometry and nomenclature. We talk to each other about aircraft and how aircraft are described. Our aircraft roughly have the same parts on them. We have a wing. Normally we refer to the wing either as the left wing or the right wing, but you'll also hear them called the port wing and the starboard wing from the nautical terms, where left is port, right is starboard. Beginning to get out of favour now because of the possibility of confusion, so better off calling things the right wing and the left wing, if anything. Here's our aircraft in plan view. What we see here is an aircraft, and we can describe the span of the wing as the distance between one wingtip and the other, and that's the span of the aircraft. The distance from the centre line to the tip of the wing is the semi-span. Looking at the wing in plan form, what we see is that we can have various different lengths associated with what's known as the chord of the wing, the distance between the leading edge and the trailing edge. That's normally referred to as the chord of the wing, but we also have what's known as the root chord, which is the distance from the leading edge to the trailing edge where the wing enters the fuselage, and the tip chord, which is the distance from the leading edge to the trailing edge at the wing tip. We also have sweepback sometimes, and we can refer to this as the leading edge sweepback. And the leading edge sweepback is the angle made between the leading edge and a line perpendicular to the centre line of the fuselage. The wing can have the leading edge swept, but we can also sweep the trailing edge if we want. There's also an angle which is referred to as the quarter chord sweepback, and that's the angle between the line drawn at 90 degrees to the centre line and a locus of points drawn 25% back from the leading edge of the wing, essentially the quarter chord line. And the quarter chord sweepback angle is the angle made between the perpendicular and the quarter chord sweep line. This is more important with aircraft that are going to travel transonically, because it's this sweepback angle which tells us whether a wing is aerodynamically swept or not. So if we look at this aircraft, which is I think the X5, which had a variable sweep wing, we can see that the quarter chord sweepback is gradually being increased from quite a low value to a high value, and it's that sweepback which allows the aircraft to travel transonically and reduces the transonic drag rise. If we look at this aircraft, which is the YF-23, which was a fighter prototype that never went to manufacture, what we see here is a wing which is highly tapered. So the root chord is much bigger than the tip chord, so it's a highly tapered wing. But if I draw a line 25% back from the leading edge of the wing, what I would see is that that quarter chord sweep line is not actually swept very much. And so this wing, while highly tapered and with a large sweepback angle on the leading and trailing edge, is aerodynamically not swept because the quarter chord line is not swept back. And the reason for this aircraft is designed to fly supersonically, and when you're flying supersonically you don't actually want sweepback. You only want sweepback to get through the transonic drag rise. So this aircraft, designed for what's known as supercruise, cruising supersonically, has a wing which is not swept aerodynamically. But for gliders, we don't normally have to worry about that much. But that's just a by the by. And that's how we would describe the shape of the wing in plan form in terms of span and chord. If we take our wing and slice it vertically, we can see the airfoil section of our wing. And what we see here is an airfoil section. It has a certain chord length and it has a certain thickness. This is a symmetric wing, and we can tell it's symmetric because if we draw a line which is equidistant from the top surface and the bottom surface, that line stretches from the leading edge to the trailing edge, and the line from the leading edge to the trailing edge is known as the chord line, and that line for a symmetric airfoil is equidistant from the top surface and the bottom surface. Now, most of the wings that we fly with are not symmetric. The main wings are never symmetric unless we're going to create something which needs to fly the same upside down as it does the right way up, such as an aerobatic aircraft. They might have a symmetric airfoil for the main wing. For our gliders, we tend to fly the right way up most of the time, and therefore our wings have something which is known as camber, and we'll go into that in a moment. The surfaces which have symmetric airfoils are the fin and sometimes the tail plane. So as I say, most of our airfoils have what's known as camber, and here we have a cambered airfoil. So again, we have the chord line of the wing, which is the line from the leading edge to the trailing edge. That's our chord line. But now if I draw a line equidistant from the upper surface to the lower surface, we would see that that line no longer lies on the chord line, but instead is raised above it. And the amount that this center line is raised above the chord line is what's known as the camber of the wing, and therefore the wing is known as cambered. And this is a cambered wing. Essentially it's a kind of symmetric wing but twisted. And here we see on, I think it's a DG 505, where the wing has been taken off, we can see the airfoil section at the wing root, and we see that the airfoil section of this aircraft is highly cambered. That if I drew a line equidistant between the upper surface and the bottom surface, it would not lie on the chord line, it would be raised above it, and there we have our cambered wing. The reason we like a cambered wing is that at low angles of attack, because of the camber, it generates a lift force, and it generates that lift force efficiently, essentially with low drag. And so by cambering a wing, the more camber we put onto the wing, the more lift we generate for the same angle of attack. Some wings are very highly cambered, and here we see a Formula 1 rear wing, and we see a very cambered airfoil. Suffice to say, in order to fly efficiently, we like a cambered wing because it gives us low drag for the lift that we want to produce. Now there's another term that you'll come across quite frequently if you fly gliders, and it's to do with the ratio between the span of the wing, the distance from wingtip to wingtip, and the chord length of the wing, the distance from the leading edge to the trailing edge of the wing, and that's our aspect ratio. So if I have a large span and a small chord, I'll have a large value of the aspect ratio. And if we look at our gliders, we tend to see that we have a large span and a small chord length, and therefore a large aspect ratio. Typically anything from about 20 up to about 50 nowadays. If we look at aircraft other than gliders, such as a fighter aircraft, what we see here is that the aircraft has a low aspect ratio. So we have a small span and a large chord. Now these aircraft are designed for different things. This aircraft is designed for maneuverability and high speed, so it wants a low aspect ratio. This aircraft is designed for high aerodynamic efficiency and low maneuverability, and therefore we have a high aspect ratio, because a high aspect ratio, when we look at drag a little bit later on, gives us what's known as low induced drag. Now there's two angles that we need to consider when we're flying, and these are known as the angle of incidence, which is the angle that the chord line of the wing makes to the free stream. And as we gradually increase our angle of attack, we will increase the amount of lift that our aircraft generates. And so angle of attack and lift are related. And the amount of lift we need to generate is also dependent on the speed at which we're flying. And therefore the angle of attack and the speed at which we fly are also linked. So at low speed we fly at a high angle of attack, and at high speed we fly at a low angle of attack. But again, more on this later. Our other angle that we need to consider is what's known as the side slip angle. And the side slip angle is the angle that is made between the free stream and the center line of the fuselage. Normally we want to fly with our side slip angle of 0, because then we're flying efficiently, and that's why we like to have the string pointing back down the canopy, because it shows us that we're flying at 0 side slip and we're flying efficiently. Now this side slip angle, sometimes referred to as the yaw angle, is kept to 0 as much as possible. The only time when we deliberately fly with the aircraft yawed is when we're having a crosswind landing and we need to point the aircraft down the runway, and therefore we yaw the aircraft just as we're about to land. The other time we might have an angle of side slip is if we're actually what's known as side slipping the aircraft, flying deliberately inefficient to increase our rate of descent. Now we have to be careful that we know the difference between the angle of attack and the pitch angle of the aircraft. So here we have two aircraft looking like they're both flying at high angles of attack, and indeed the aircraft on the right hand side, we can see by this little vortex which is being shed from the nose of the aircraft, and in the core of the vortex we get a low pressure and the water vapor is condensing out, so we can trace the vortex and we can see that indeed the aircraft is flying at a high angle of attack, about 15 to 20 degrees. The aircraft on the left is in climbing flight, and what we have here is that the aircraft's what's known as pitch angle, the angle the aircraft makes relative to the horizontal or the ground plane, is around about 80 degrees. But the aircraft itself would still be flying at a relatively low angle of attack, and between about 4 and 6 degrees. So do note the difference between angle of attack and pitch angle. And where we see this most is in a loop. So here we have an aircraft looping, and what we see is that the aircraft's pitch angle is changing through 360 degrees. So the angle relative to the ground plane changes through 360 degrees. But the angle of attack during that maneuver is still probably only between about 4 and 8 degrees. We normally fly at around about 4 or 5 degrees angle of attack. When we're flying slowly, we're probably getting up to about 8 to 10 degrees angle of attack. And when we stall the aircraft, we're probably in the region of 12 to 15 degrees angle of attack. Now the other thing we're going to have to talk about here is the control surfaces. Now we control the aircraft by using the elevator, the rudder and the ailerons, and they give us control in pitch, yaw and roll. So the rudder gives us control in yaw, the elevator gives us control in pitch, and the aileron gives us control in roll. Now the way that our control surfaces work is they change the camber of the section. So if we consider an aileron out at the wing tip, what we see is that if we deflect the aileron down, we generate more camber, which creates a force in the upward direction. If we deflect the aileron up, we generate more camber again, but in this case it would generate a force in the downward direction. Say we want to roll the aircraft to the left. On the left wing, the aileron would be deflected up, generating a down force, and on the right wing, the aileron would be deflected down, generating an up force, and therefore generating a rolling moment, which rolls the aircraft to the left. For the elevator at the back, deflect the elevator down, generates an upload, pushes the nose down, tilt the elevator up, and we generate a download which will push the nose up. And the same at the rudder at the back, deflect to the left and it will push the nose to the left, deflect to the right and it will push the nose to the right. And so we can control the aircraft in all three axes. The other surfaces that we might have that we'd like to consider is the air brakes. Now the air brakes don't do what they say. They don't actually brake the aircraft. We don't use the air brakes for slowing down. We use the air brakes to generate more drag, and because they generate more drag, they increase the rate of descent and therefore steepen the glide slope when we're coming in to land. The other surface we have is flaps. Now we'll go into what flaps do in a later lecture, but essentially again all they do is change the camber of the section and change the way that the lift is generated. Our other two surfaces are stabilizing surfaces. The fin gives us stability in yaw, so if the aircraft is disturbed in yaw, the fin tends to pull the nose back to where it was before, and the horizontal stabilizer, the tail plane, generates stability in pitch. So if the aircraft pitches nose up due to a gust or something, the horizontal stabilizer will tend to push the nose back down, and it makes life flying the aircraft much easier and allows us to fly the aircraft, if we've got it trimmed out, hands off.